So, welcome back students. We are basically discussing functional group based strategies, and we talked about how to introduce key appendages which are basically hanging functional groups, and now we will trying to discuss on the same topic, and the next problem which is we will be trying to analyze is a simple problem, but here couple of other things also we will be discussing. This compound which was given as a target molecule having a aldehyde as well as another aldehyde is basically dialdehyde compound. The stereochemistry was given as a cis for both this 1,2 di substitution. The starting material which was also given to you having a structure of this type, this is OH, yeah. Now, if you analyze closely, the stereochemical point of view we will be just talking here that this particular hydroxy stereocenter was inverted in this starting material, but the appendages have been changed. Here you are having a hydroxy appendages, here you are having a aldehyde appendages. So, need to do a kind of a inversion reaction to introduce some functional groups which can be later on converted to a CHO functional group. Now, we do the very conventional retro by doing a simple FGI, and we already discussed that aldehyde appendages can easily be constructed if you having corresponding cyano compound by a diball reduction. This is basically reductive transformation. So, cyanide can be converted to a diball to the corresponding aldehyde. Now, if you have a dicyano compound, now you try to correlate that how this dicyano can be converted or can be accessed from this dihydroxy compound. Now, I say we will be doing a simple FGI where if you have the O mesylate as well as this mesylate. Now, this we put a dotted line because you say that this step you need a inversion because this is a 2 degree carbon and this is a primary carbon. Now, try to correlate that this is a dihydroxy compound. You can easily convert to this dihydroxy compound to a dimesylate. Now, we will analyze that how this conversion can easily be achieved. So, start with the starting material which was given to you, this hydroxy was below the plane and this primary one is above the plane. The starting material was given to you. Initially convert to this by treating with a mesyl chloride triethylamine excess, because you need to convert both the hydroxy to its dimesylate. Now, mesylation definitely is a SN2 reaction, but as it does not touch the carbon, it will basically the stereochemistry will remain intact. Now, what is mesyl chloride? Is a methane sulfonyl chloride. You need a base to basically make it O minus, this O minus will now attack to this sulfur here and you get a new oxygen sulfur bond. Now, as here you did not touch the stereocenter, SN2 will be taking place, but there will be no inversion. Now, next will be subject this molecule to a sodium cyanide excess, because you need to convert both the mesylate to corresponding cyano. Now, sodium cyanide basically a source of cyanide which is also very strong nucleophile. Now, this cyanide will touch here. Now, for this one you are now making a new carbon carbon bond, because you are introducing cyanide. Now, here by using a strong nucleophile sodium cyanide in excess, in this case SN2 starts fine, but here also SN2 is occurring, and particularly this point, if SN2 occurs, you have a inversion here, and this case there is no inversion. So, particularly this point, the appendage when you are introducing by a displacement reaction, it undergoes inversion, and this was the main key factor. And then now, as you are having this diacyanide, you do a excess diol treatment to complete the synthesis in a efficient way. So, your target molecule is basically achieved. So, whenever you have a stereochemical issues, you can basically address it by a standard reactions, and if the reaction mechanism demands that your inversion will takes place, particularly as I said here, the secondary carbon will undergo SN2 inversion, the backside attack, which is very common in SN2 cases. Then you can access the target molecule. The same line we will be now discussing another related problem based on the appendages disconnection. We will give you a target molecule whose structure is this. The starting material was also given to you. The only difference is this starting material having a vinylic appendage, which is now converted to a allylic appendage, 1 carbon extension, and the allylic end has been now required a deuterium. 2 of these hydrogen now have been replaced with deuterium to give you a little bit more synthetic challenges. Okay. So, we will now do a straightforward retro how these things can be done. Now, I say if you do a Wittig kind of transformation based on this functional group or the appendage functional group which is present. Now, what kind of Wittig elite you will be using here? As deuterium is required as the final compound, you can probably think about if you use this Wittig elite which is having deuterium here. Now, this Wittig elite you can easily prepare if you have CD3 iodide in presence of like similarly earlier problem we have talked about if you have a methyl iodide. Now, here you replace hydrogen with deuterium and react with triphenyl phosphine to get a Wittig salt, and then you treat with base to complete the Wittig transformation. So, basically you need to now convert this aldehyde and try to correlate how this aldehyde can be accessed from the starting material. Now, this aldehyde can be constructed if you have a primary alcohol. Now, here this is a oxidative based transformation, any oxidation suitable oxidizing agent, and then here you now try to correlate with the starting material if you do a hydroboration reaction with boron THF. So, you can now come to your starting material. So, the forward synthesis which will be very simple, you start with the starting material which is having the vinylic appendage. You do the hydroboration with boron THF, okay. And then you find that this hydroboration will give you the primary alcohol. Next, as you shown in the retro, you convert this compound to this corresponding aldehyde. Then your Wittig reaction will be in action with this deuterium based elite which you already prepared from CD3I and triphenyl phosphine. Now, you see you will be able to construct the target molecule with the required allyl appendages, and the allyl appendages having deuterium at its final terminal. So, this way you can basically simply construct the appendages based on your requirement, and simple transformations will be always preferred. The next problem which we will be now discussing, it is little bit tricky. We have given you a lactone as a target molecule. This lactone basically having a 5-member lactone with a allyl appendages, stereochemically pure allyl appendages. But the starting structure, if I give it to you, then you will be little bit perplexed or little bit confused that how this starting material will be converted to this target. I say the starting material which I will be giving to you is this starting material. Now, you try to correlate that this starting material is having some extra group or extra additional appendages like this TBS group, which was not present in the target molecule, as well as you see this ketone having a allyl appendages here, but in the final product this allyl appendages somewhere 1 carbon away from this ketone. Now, this way if you first take the target molecule and try to figure it out how this target molecule can be retrosynthetically disconnected. We will say the retro will be, if we having a compound something like this, which is basically nothing, is called lactol or basically hemiacetal. Now, this is a hemiacetal where you have a secondary hydroxy group. So, if you have this intermediate, you do a simple oxidation here to give you the lactone with this required allyl appendages. Now, this lactol you need to construct how this lactol is correlated with your starting material. Now, lactol is basically nothing, is a hemiacetal as I already said, and then now you will just do a simple FGI based things. The allyl appendages is here. Now, see if you having a hydroxyaldehyde, hydroxyaldehydes are basically this kind of compound. Hydroxyaldehyde will undergo lactol formation by just this kind of attack, will give you the lactol. Now, this hydroxyaldehyde which was proposed as one of the intermediate, now we have to correlate with the starting material. The hydroxy appendages, now we need to focus it out how this hydroxy appendages will be now we now come to intermediate which is little bit unconventional, but we said that if you have this kind of compound where is a 1,2 diol functionality is there, the 1,2 diol functionality you can definitely do a oxidative cleavage by Johnson-Lemieux reagent to give you this hydroxyaldehyde. Now, there are 3 hydroxy group, this is the isolated primary one, this is 2 or 1,2. Normally, for this Johnson-Lemieux oxidative cleavage only 1,2 dihydroxy compounds are cleaved. Now, why we drawn this intermediate? Basically, now if you count the number of carbon, this is 1, 2, 3, 4, 5, and the target molecule also is given 1, 2, 3, 4, 5. So, basically trying to trying to analyze that how this particular carbon or this particular intermediate is linked with this starting material, and then now you try to figure it out how this intermediate is related to the starting material. We say that if you have the starting material, you just simply do a reductive cleavage. Reductive cleavage means you do a reduction. Now, this reduction will basically give you a allyl here, This is basically carbonyl group which will be reduced to alcohol. Okay. Then here you are having this CH2OH, and this TBS group also can be thought that it can also give you a particular OH by TBS deprotection. So, now you complete the synthesis through a forward pathway. Now, start with the starting material which was given to you. The starting material which was given to you is having this structure TBSO. So, first we will be using lithium aluminum hydride, which is a strong reducing agent. Your allyl will be here and you will be having a OH here, and then basically I think the starting material was okay. The initial starting material which I have earlier drawn is actually little bit wrong. Starting material was given. You can actually the starting material was, that is why the retro was not coming properly. It will be particularly this starting material. Yeah, fine. So, now this starting material which is okay, we will just draw the starting material again, and then we will find the starting material was this one, and you are having this TBS here. So, do a lithium aluminum hydride reduction, and then you will find that this allylic group will be there, and you are having this primary hydroxy. Now, this is after cleavage it will give you this OH and this O TBS. Now, TBS can selectively be cleaved by HCl treatment, that will now give you the diol, which is next required for this oxidative cleavage. So, allyl appendage is there and you are having this CH2OH. Now, what you do? You just treat with sodium periodate. This is a 1,2 diol, 1,2 vicinal diol, which is now going to be cleaved to give you a aldehyde. Your allyl things are remaining here and you have this CH2OH. Now, see, we have drawn the intermediate correctly, but as the starting material was not given correctly in the initial drawing, it was bit difficult. So, now you can basically visualize the starting material. So, now we are here after this chopping of this diol. Now, basically what you need to do? You just, this ring will be automatically closed because this is a hydroxy group and aldehyde group is there. So, lactol formation or hemiacetal formation will take part with this alcohol, and this will get this OH. So, basically one carbon was removed by this diol chopping. Now, see, you do a oxidation which will now complete the synthesis as desired. So, this is now the target molecule. So, as the initial drawing was little bit wrong, you just try to get the correct structure of this particular starting material, which is now this starting material. So, eventually this kind of functional group adjustment and how this particular appendages are linked will give you a clear cut idea that how the pathway can be eventually generated. A similar kind of analysis will be now next doing, where the target molecule was, you are having a alkyne functionality, you are having a methoxy here, and then you are having this 4 CH2OH group. We will just now give you the target molecule having CH2, 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 OH. So, this is the target molecule which was given to you. The starting material was a lactone which was given to you, starting material. So, try to count the number of carbon. This is a 1, 2, 3, 4, 5. The O-methoxy is there, O-methoxy is there. Now, in the target you are having 1, 2, 3, 4, 5, 6. So, basically you need to introduce 1 carbon extra and you trying to having a alkyne functionality at one of the terminus. So, this basically gives you a some thought that how this alkyne functionality can be created at one end. Now, take the starting material first, and if we try to do the target in this way, that we say this compound will write in a different way, that 3 carbon CH2 is there and you are having this OH, and somehow if you are having a aldehyde functionality here, aldehyde functionality. Now, this is 1, 2, 3, 4, 5, which is exactly the starting material. Now, this kind of hydroxyaldehyde normally do not exist as a linear form, they will seem to be occur in this lactol form or a hemiacetal form. So, lactol is basically nothing, but when it is opened up it gives you a hydroxyaldehyde. So, only thing is you need to now convert a synthetic, or you need to think about a synthetic transformation where you will get a alkyne functionality starting from a aldehyde. Now, for that we will talk about a transformation which I am sure we have not discussed. The transformation is basically named as Corey-Fuchs transformation. It is basically a name reaction, Corey-Fuchs transformation. This is a unique transformation. The synthetic steps which you can think about for this Corey-Fuchs transformation, you react this thing with triphenyl phosphine and CbR4 in presence of the aldehyde and react with butyl lithium, we basically end up with this alkyne. So, that is the transformation now we will be talking about. Now, how this reaction takes place? So, initially it is a Wittig type of reaction. Initially triphenyl phosphine and CbR4 react, basically give you PH3P plus, Br minus and CbR3 minus is also generated. Now, this CbR3 minus attacks to this phosphorus positive thing, and basically now you are getting PH3P plus and this Br, Br and Br. Now, the remaining Br which is remaining triphenyl phosphine is there, triphenyl phosphine is there, and this triphenyl phosphine is now attacking to one of these bromine to give you a intermediate which is now formed as a something like this. Now, actually in principle this is nothing a Wittig type of reaction. You remember in Wittig case we treat with triphenyl phosphine with any of this alkyl halide or alkyl bromide or alkyl iodide to get this kind of ylite. So, this is basically nothing the kind of a ylite which you generate from triphenyl phosphine and CbR4. Now, react with this aldehyde with this ylite. By a similar Wittig mechanism you basically will get this dibromo species. Now, this dibromo normally was not isolated, you react with N-butyl lithium. One of this lithium will be exchanged with this bromine to give you the vinylic lithium species. Now, this vinyl lithium species will not be ideal, it basically try to react in this way with the loss of this bromine to give you a carbenoid kind of intermediate where you have this negative charge. Now, this carbenoid intermediate will then undergo a rearrangement. I will again draw this thing, this particular intermediate it is now try to give you a hydrogen migration and this rearrangement is named as Colvin rearrangement. Colvin rearrangement to give you a alkyne which was the main reaction. So, now try to figure it out how this transformation can be carried out. You start with initial this compound which was given to the starting material, first react with dibal. Dibal is a selective reducing agent that will basically reduce only the lactone to lactol. Sorry, the oxygen is here, this is a carbon. So, now this lactol basically try to open it up. Lactol is basically nothing, it is the hydroxyaldehyde. So, now if this opens up, you are basically getting this 3 CH2, 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 CH2. So, you are having CH2, 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 OH and this aldehyde. Now, you do the Corey-Fuchs reaction, the Corey-Fuchs transformation which I have just now discussed. You basically now get the these things as a alkyne and your CH2, 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 OH. So, this is the target molecule we have initially set up. So, in this transformation you will find that a particular alkyne appendages or alkyne functional group was introduced and the retrosynthetically any alkyne of this kind of structure you can basically construct from a corresponding aldehyde in a one step transformation by using a Corey-Fuchs reaction or Corey-Fuchs reaction or CF transformation. Now, for detailed mechanism of this step you can basically go to scenarchive.com which you have told you in the beginning that scenarchive.com will give you a list of name reaction and base transformation and Corey-Fuchs is a very important reaction. So, in this way basically you can try to get access of a alkyne starting from a aldehyde. So, we will keep on discussion of our appendage based strategies or functional group based strategies in next week also. Until then we just study and go through the assignments. We will again catch you later on in the next week. Bye.